zeolites, impact of acid sites characteristic on catalytic performance. This is contribution from the Institute of Physical Chemistry from Kiev and Sorbonne University Laboratoire de l'activité de surface in Paris. The context of my work is related with zeolites and with transition metal introduction in the zeolite framework as isolated centers, because this is possible to create active site in the zeolite for different catalytic processes. A zeolite catalyst with isolated center is difficult to obtain due to a specific problem related to two starting components, solid and metal precursor. Because in the zeolite, different metal species can be formed in metal oligomers, metal oxides, isolated framework, and extra framework metal species. This is a metal structure, and there is the question where different metal sites can be formed in the zeolite. There is several possibilities, but the main is isolated extra framework sites. This is formed here. Extra framework metal oxide, but the most interesting is incorporation of metal in the framework position as isolated framework species. But this is very difficult to obtain this situation. So today I would like to show you, as I try to incorporate the metal species in the framework position of the zeolite. And after we will look for the catalytic activity as obtained catalyst. So the objective of this work is to incorporate transition metal in the framework of zeolite with formation of mononuclear transition metal and obtain metal single site materials. With application for different reaction such as oxidative dehydrogenation of propane or biomass valorization. To reach this objective, two-step post-synthesis method will be developed by me in the past, and by controlling the preparation condition, pH and metal precursor concentration, we can try to incorporate the metal species in the framework position of zeolite. Advantage of such preparation is to restrict the speciation of transition metal in the catalyst to a single mononuclear species. In the first case, I would like to show you how to incorporate vanadium in the beta zeolite using two-step post-synthesis method, which consists in the first step removal of aluminium from the structure of zeolite by treatment with acidic solution, then formation of vacant site. Then in the second step, ammonia metabolite was contacted with this zeolite, and the reaction takes place between vanadium species and vacant site, and incorporation of vanadium takes place. So this is very easy to show by scheme, but more difficult is to confirm that this work. So in if we were in pH 2.5, so this is the region of predominance of vanadium species in the solution of ammonium metavanadate. So we can see that only at low pH 2.5, for example, we observe in the solution VO2 plus species, small species, and this species can be contacting with Zn-BEA zeolite after dehydrogenation, and very large peak band at 3,520 is disappeared. This confirms that the reaction takes place between vacantic site OH and VO2 plus species. So we can observe disappearance of this band and consumption of this band. So this means that reaction takes place between VO2 plus and OH with incorporation of vanadium in the primary position of zeolite. This means the specific reaction between vanadium precursor and the silanol groups takes place. Now, using different technique, we can confirm that really incorporation of vanadium into vacantic sites takes place at pH 2.5. So, in this condition, we can see that at pH 2.5, there is specific event related with presence in the solution of ammonium metavanadate VO2 plus, and this VO2 plus, this peak is disappearing in function of contact with Zn-BEA zeolite. So this peak, intensity of this peak is decreasing and disappearing completely. At the same time, we observe in the solid NMR, vanadium mass NMR, appearing new band at minus 620. This band is related with the formation of vanadium tetrahedral species. So this shows us that reaction takes place between VO2 plus and OH of Zn-BEA with incorporation of the vanadium as vanadium tetrahedral species. This result was also confirmed by UV zip spectroscopy. So we can see here that UV zip spectroscopy shows us for the low loading of vanadium, there is only two bands corresponding to oxygen tetrahedral vanadium charge transfer transition involving bridging the OSE oxygen, this one, and this second band at 140 corresponding to oxygen tetrahedral vanadium charge transfer transition involving the oxygen. This one, the oxygen. And this two band is present in the vanadium tetrahedral species. But with increasing of the vanadium loading, we can observe that new one species is observing is corresponding to oxygen octahedral vanadium charge transfer transition. This means that plus in the zeolite there is formation of octahedral species in the extraflammable position. Now, what happened when we change the pH and concentration of the precursor? What happened in this condition? We can see that when we change pH, from 2.5 to 6. In the solution, we can observe not only mononuclear banana species, but also polynuclear banana species. So, in this situation, it will be more complicated to incorporate all vanadium in the ground position. So this is confirmed by the infrared spectroscopy, because in the case of preparation at pH 2.5, we have nice poor resolved band to band corresponding to the presence of vanadium tetrahedral species. In contrast, at pH 6, we have, in addition of tetrahedral banana species, we have octahedral species, etc. So this species is more complicated, and we have not observed a very good spectra. It's confirmed that in this condition, some part of vanadium is incorporated in the extra-thermal position. So this means that preparation at pH 2.5 is better for obtaining single-site materials.
There's no way.
This is confirmed also by UV visible spectroscopy. In this case, also we can show that already for low loading, we observe octahedral species related to the presence of vanadium in extra-thermal position. So, influence of pH on the incorporation of vanadium in the zeolite is confirmed also by silicon mass NMR. Here, present here, we can see that in the case of silicon mass NMR, we have here the band corresponding to the formation of the hydrogen bonded OH, and when we incorporate vanadium, this band disappeared completely in the case of preparation pH 2.5. In contrast, in the condition of pH 6, this band is not disappeared completely. It means that in party of OH is still present, not occupied by vanadium in the case of preparation pH 6. So we can see that condition of preparation of the catalyst is very important. So we should know about this before starting the preparation of the catalyst for the different reaction. Also, by EPR spectroscopy, we can see that in the case of EPR spectroscopy, when we prepare the catalyst and use in ODH test, so we can form vanadium form signal, this characteristic here, and when we simulate this spectra, we can found that ratio of tetrahedral to octahedral species is 10. It means that practically in this condition, in pH 2.5, we have practically all vanadium in the thermal position as vanadium for tetrahedral species after ODH reaction. In contrast, when we prepare the catalyst in pH 6, so ratio tetrahedral to octahedral species present in the zeolite is 0.5. It means that major party of the vanadium 4 is present in the as octahedral vanadium species. Now we use this catalyst for oxidative dehydrogenation of propane, and we can see that when we were in pH 2.5, for vanadium Se beta zeolite, we have 10 times of higher propane rate formation than in the case of preparation of pH 6. 10 times higher rate, and also turnover frequency is 10 times higher here than here when we prepare it at pH 6. So this show us that preparation, condition of preparation of the catalyst in the case of vanadium is very important, because in pH 2.5 we have more active catalysts with high selectivity for propane formation. In conclusion of this first party, I would like to tell that at pH 2.5, predominant monopolar vanadium VO2+ ion react with the SiOH group created through desalination and led to the formation of pseudotetrahedral flower vanadium species. At pH 6, mononuclear polynuclear vanadium species is formed. Turnover frequency of the propane oxidative reaction of the zeolites exhibited flower species 1 order magnitude higher than those in the zeolite exhibiting extra flower vanadium species. It means that isolated pseudotetrahedral vanadium species will be active sites of OTH reaction. So here we can show that these sites present in the flower zeolite is active sites of oxidative dehydrogenation of propane to propylene, not the big species present as vanadium oxide. Now I would like to show you a second application of the catalyst prepared with the similar two-step process method when we incorporate zinc in the beta zeolite. In this condition, in the second step, we incorporate zinc in the vacancy site formed by the removal of aluminum in the first step by treatment with acid nitric. So in this condition, we form also vacancy site, and this vacancy site is contacting with zinc precursor. We show you that after this reaction, zinc is incorporated in the flower position of the zeolite. This kind of catalyst will be applied in dehydrogenation of propane to propane with CO2 as mild oxidant. So the application of the zinc beta zeolite in this work can show us influence of the preparation of desalinated zeolite and incorporation of zinc in the flower position, because when we desalinate and incorporate zinc, we form different acid-base characteristic in the Zn beta zeolite, and we will see that the catalytic property will be changed in function of this. So we prepared 3 kinds of Zn beta zeolite: Zn beta without desalination, Zn SC beta partially desalinated catalyst, and Zn SC beta series. In this case, we incorporate 1% for all catalysts. We incorporate 1% of zinc to see catalytic activity of the catalyst with similar content of zinc. So then we can use several physicochemical techniques to confirm this characteristic and show effect of the different acido-basic property on the catalytic activity of such catalysts. In the first, we can I can show that this diffraction pattern for the three kinds of catalysts is very similar. So it means that dehydrogenation and incorporation of zinc in the zeolite is not going to destruct of the structure, and when with incorporation of the zinc in this free support Al beta, Al SC beta, and SC beta, we form zinc Al beta, zinc Al SC beta, zinc SC beta catalyst with microporous and mesoporous property. Then silicon mass NMR of this sample confirm that in this case we form very similar pattern of zeolite. Now using ammonium TPD and CO2 TPD, we can show that we can obtain information about concentration of acid sites and concentration of basic sites. So we can see that full dehydrogenation of beta following by introduction of zinc into vacant site of zeolite result in reduction of the total acidity, as we can see here, and having different kinds of weak and medium basic sites. By adsorption of pyridine, we can check the nature of the acid sites present in the Zn beta sample, this one, this, and this. So we can see that in the case of Zn al beta, we have broad acid site, which is characteristic by this band, and Lewis acid site. And when we dehydrogenate al beta zeolite and obtain zinc SC beta zeolite, in this case, we haven't broad acidity, and we will see what happened when we use this this kind of catalyst for the our reaction. Here we can see that higher value of propane selectivity is obtained for Zn SC beta zeolite, and with 90% of selectivity to propane, and with yield of propane formation about 30%. Then we can see influence of the presence of the CO2 and absence of the CO2 in the mixture during the reaction. This is shown that with CO2, introduction of CO2 into the reaction mixture, decreasing the apparent activation of propane formation from 124 kJ per mole to 110 kJ per mole over the Zn SC beta catalyst. And then by using PPD of propane and propylene, you can see that propane and propylene, you can see that the surface of Zn al beta has the highest number of centers capable of retaining propane and propylene. And in the case of normalized O2 TPO profile of Zn-beta catalyst, we can see that in the case of Zn-beta, there is practically no formation of the coke, because coke is formed on the bronchial acid sites present in the presence in the zeolite when aluminum is present in the flammable position. So now we can show what happened with full delamination. So with full delamination of the zeolite, bronchial acid sites is eliminated, and in this condition we can see the highest selectivity of propylene in the case of Zn-beta zeolite, and it means that in the presence of bronchial acid sites, in the case of Zn-al-beta and Zn-al-beta, produced propylene can be going to side reaction with oligomerization and cracking followed by coking. So in this condition, the selectivity is much higher, much lower in the case of Zn-al-beta and Zn-al-beta, because there is a side reaction which takes place when the propylene is formed in these two cases. So selectivity about 90% is obtained on the zeolite Zn-beta in the absence of bronchial acid sites. In conclusion, I would like to tell that the post-synthesis procedure preparing 1% of Zn-beta catalyst sample, including preliminary delamination process and following the introduction of Zn2+ cation into vacant site of zeolite, leads to the reduction of the total acidity of Zn-beta compared to Zn-beta, and having the total basicity of Zn-beta. So this means that in the case of Zn-beta catalyst, which is the best catalyst for propylene formation, there is a specific basic sites, and in absence of bronchial acid sites, we can form a lot of propylene. In the presence of Zn-beta catalyst, the achieved selectivity of about 90% and yield of 30% related to the propylene in the CO2 propylene dehydrogenation process exceed those for Zn-al-beta and Zn-al-beta. So positive effect of fuel delamination on selectivity lower deactivation with increasing dose is mainly attributed to the lack of the bronchial acid site. So the first process, means delamination, is very important for preparation Zn-beta zeolite without bronchial acidity, but with specific basic acidity. Thank you very much for your time.